o'clock at night, you walk out the door. You told me, baby, you was going to the drugstore. But in my mind, I knew you was lying. The drugstore closed at 8:45. I said, I saw you kissing Willie across the fence. I heard you telling Willie I don't have no sense. The way you've been acting is such a drag. You done put me in a trick bag.
Every text on rigid body motion follows Euler's equations with a section on gyroscopic motion. One reason is that the equations of motion for gyroscopic motion can be solved analytically, and I'll give a link to a video with the analytic solution in the description below. Another reason is that gyroscopic motion is amazing and counterintuitive to the uninitiated. In this video, we'll look at gyroscopic motion from 3 angles. First, we'll see what Newton's laws predict. Then we'll look at the equations of motion as implemented in our rigid body simulator from the last video, which we'll use to model a gyroscope. And finally, we'll explain gyroscopic motion without any mathematics whatever. The picture is a screenshot of a video of an MIT class on gyroscopic motion taught by Walter Lewin, and it shows a spinning bicycle wheel that is supported by a single rope. The spinning wheel doesn't fall, but instead rotates slowly around the rope. It only starts to fall after the spin rate has slowed considerably. So, how can we explain this seemingly bewildering and counterintuitive behavior of a spinning wheel? First, let's see what Newton's laws of motion have to say about the subject. The diagram shows the forces acting on the wheel. The two forces are equal and in opposite directions, so the sum of the forces acting on the center of mass of the wheel is 0. From Newton's second law for translational motion, the center of mass of the wheel does not accelerate, and hence the center of mass of the wheel remains stationary. The forces create a counterclockwise torque from our perspective on the wheel, which is a negative torque around the y-axis. The magnitude of the torque equals F times d, where F is the applied force and d is the length of the axle from the wheel's center of mass to the point of application. From Newton's second law for rotation, the applied torque equals the derivative of the angular momentum as shown in equation 1. We'll assume that the wheel is spinning with the top of the wheel receding from us. That is, the angular rate vector has components omega sub x, 0 and 0, and omega sub x is negative. The angular momentum for the wheel is shown in equation 2, and it is also pointing along the negative x-axis. From Newton's second law for rotation, the applied torque T equals the derivative of angular momentum dl dt, and hence dl equals the applied torque times dt as shown in equation 1. The diagram shows the angular momentum vector and its incremental change dl, which points in the negative y direction. So we expect the angular momentum of the wheel, which points along its spin axis, to rotate toward us, just as it happens in the Lewin video. So Newton's laws of motion account for the seemingly bizarre motion of the spinning wheel. In the previous video, we implemented Euler's equations of motion for a rigid body derived from Newton's laws in a rigid body simulator. So we will simulate gyroscopic motion. Euler's equations are applicable if the rigid body has a diagonal moment of inertia matrix. A wheel has rotational symmetry about its spin axis, and hence the moment of inertia matrix is diagonal. The moments of inertia for a spinning disk are 1/2 mr squared for the axis of rotation and 1/4 mr squared for the other two axes, where m is the mass of the disk and r is its radius. To simulate the wheel configuration, we need to generate the applied torque, which has constant magnitude and points in the direction perpendicular to the inertial z-axis and also perpendicular to the spin axis. That is, the torque points in the direction of the cross product of the inertial z-axis and the body x-axis. So let's give it a spin. The video shows the body axes of the wheel along with the trajectory of the point at the top of the wheel. Oops, wait a minute. That didn't look right. The sim seemed to be okay for a while, but then it went south. One of the problems that sometimes occurs using Euler's method is that errors accumulate, especially if the motion's repeated. That could be what went wrong here, so the first thing to do is to try a smaller step size. Now we'll try to understand gyroscopic motion from an intuitive perspective. The diagram on the left shows the forces exerted on a spinning wheel when a negative torque is applied along the y-axis. The diagram on the right shows the forces looking from a point directly in front of the wheel. It looks, at first glance, like the torque should rotate the wheel counterclockwise about the y-axis. Now we'll look at the trajectory of a point at the top of the wheel for 2 revolutions. For the first revolution, the wheel will spin around the x-axis with angular rate vector omega x 0, 0 with omega x negative. For the second revolution, the angular rate vector has an added omega y component, that is, the angular rate created by a torque as shown. We'll see that the effect of the added omega y component doesn't rotate the wheel around the y-axis, as you might expect. Instead, it rotates the wheel around the z-axis. During the first revolution, the wheel is spinning around the x-axis, and there is no y component to the angular rate vector. During the second revolution, the added y component of the angular rate first pushes the trajectory to the left, and then pulls it back toward the right, keeps pulling it to the right, and finally pulls it left again. We can look at the two trajectories from different perspectives and see that the effect of the added y component to the angular rate vector has been to rotate the trajectory around the z-axis. If we look at the trajectories from directly above, we can see that the first trajectory was in the yz plane, and the second trajectory was rotated around the z-axis. The assignment is to implement the gyroscopic motion simulator.
me wrong, but I know I'm right. It wasn't I that started the fight. She's my daughter, and I'm her paw. You ain't nothing but a son-in-law. But I saw kissing Willie across the fence. I heard her telling Willie I don't have no sense. When she's been acting such a threat, you done put me in a trick bag.